Alright guys, welcome to this question here about the hands of a clock moving around, as they do, move around the clock face. Okay, and the question here is saying, okay, so yeah, coming back to the question. Question was essentially saying, okay, if you've got the hour hand here, which is 6 centimeters long, and the minute hand here, which is 8 centimeters long, then there's a length formed between the tips of the hands. Now I've called that length L. Now you've also got another thing which is changing, which is the angle between the hour hand and the minute hand. Now at 9 o'clock, yes, it is pi over 2, but of course that is changing. It's not always going to be pi over 2. So I've called that angle theta. Now, you might be thinking that this is a related rates of change question, but not quite, because this angle here, okay, because a clock moves at a predictable rate, the rate at which this theta is changing is a constant. So one of the things that you should consider, okay, is the rate at which the hour hand, sorry, the minute hand is moving. Okay, what would that be? So just think about this, that this minute hand moves through a full circle, which is 2 pi radians. So the rate at which the minute hand moves. Okay, so it moves through 2 pi radians every 60 minutes. In other words, pi over 30 radians per minute. Okay, and then you've also got the rate at which the hour hand is moving. Okay, so that moves through 2 pi radians, but that takes, for it to come right back to there, that would be 12 hours. Okay, now 12 hours is 12 times 60 minutes, so 720 minutes. So pi over 360 radians per minute. Okay, now that angle theta is the angle between those two. So it's the difference then, that the rate at which that angle there is changing would be the difference between the faster moving hand and the slower moving hand. So what you need to do is you need to get an expression for the rate at which theta is changing with time. Okay, what would that be? That's one thing we're going to have to get. Now, the other thing you need to consider is, because the question says what's the rate of change of this length L here? Now, what you've got is this L here, okay, is part of a triangle. Won't necessarily be a right angle triangle. So another thing that you need to consider using is the cosine rule to get an expression for L. Okay, and you want the rate at which L is changing with time. Okay, that's enough clues, I think. So have a go, see if you can then get an expression for this L in terms of these sides here and this angle. Okay, now, and that then, okay, we need to find the rate at which L is changing. So another thing that you're going to need to use, that you can use, and one way of doing this is implicit differentiation. Okay, have a go. So pause the video, have a go, see what you can come up with. Alright guys, so welcome back. Okay, so what I'm going to do here is I'm going to get an expression for the rate at which this angle here is changing with time. And that's going to be equal to the difference between the faster moving hand and the slower moving hand. So if we put that over 360, 30 goes into 360 12 times. So we end up with 11 pi over, make sure I've got that right, yep, over 360. So that is the rate at which that angle is changing with time. It's a constant because, well, clocks move at a constant rate. And so this angle between these two would be changing at this rate here constantly. So we've got that. Now the other thing that I want to do is I want to get an expression for this length here. So I'm going to use the cosine rule. Okay, so remind you, if you have a non-right angle triangle, where this is angle A, this is side A, angle B, side B, angle C, and side C, that we can get the cosine of A would equal B squared plus C squared minus A squared over 2BC. And you can also get the equivalent expression for, say, the length of A. You can just rearrange this formula and make A the subject. Now I'm actually going to use this one here, and then because I do want a length here, I'll just make that length the subject in a minute. So let's move on to a new page here. So just to bring through some of that information, we've got this. Now, an expression for L. Okay, so I'm going to use the cosine, let's put it here, of that angle theta is equal to 8 squared plus 6 squared minus L squared over 2 times 8 times 6. This gives cos of theta, that gives 100 minus L squared over 96. Now if you make L squared, yeah, let's do this in a couple of steps. So (100 minus L squared) would equal 96 cos theta. So L squared is going to equal 100 minus 96 cosine theta. Okay, so what we can do now is we can derive this. Okay, so we can get using implicit differentiation. So we get 2L times dl over dt. I'm going to derive with respect to t. Gives not 100. Undo that. Okay, because that's a constant, and the derivative of cosine is negative sine. So we're going to get negative sine times negative 96. So it's going to become positive 96 sine theta times d theta over dt. Now we've got an expression for d theta over dt, which we're going to substitute here in a minute. And I want to get an expression for, I want to find out the rate at which L is changing with time. So we're almost there. So, yeah, let's just keep going. Let's plug in what we've got. Okay, so let's plug in this 11 pi over 360. Let's tidy that up a little bit. Okay. Times 11 pi over 360, and all of that is going to be divided by 2L. Let's move this over here. So dl over dt would equal, let's cancel out the 2's, a factor of 2 there, so it's going to become 48. What's the tidiest way of writing this? So 48 sine theta. Let's put that over L. then times it by 11 pi over 360. Okay, now expression for L. Okay, so we've got this L squared here, so L would be the square root of that, so we can write that in there. So that's going to be, what's it, 100 minus 96 cos theta. All right, so we have an expression for the rate of change of L. Okay, now the only thing now we need to do is to substitute in something that we know. So at 9 a.m., because the question said find the rate of change of that length at 9 a.m. Well, at 9 a.m. that angle is pi over 2 radians. So dl over dt, we're going to get 48. Now the sine of pi over 2 is 1, so that's just going to be 48 there. The cosine of pi over 2 is 0, so we're going to get the square root of 100 take away 0, which is just 100, and the square root of that would be 10. So this is going to be our answer. So let's tidy it up. So we're going to get 48 times 11, which is 528 pi over 3,600. Now if you simplify that fraction, you end up with 11 pi over 75. That would be centimeters per minute, because L is a length, and we're working in centimeters. Okay, so there we go. What's some of the key things to take out from this question? Yeah, one key thing to use is the fact that if you've got two things which are moving around in the circular motion here, okay, then the angle between them, the rate at which that is changing, is simply the difference between the two individual rates. Okay, another thing we need to know, we do need to know the cosine rule, and another one would be the sine rule. So if you're not sure about those, please ask. Okay, so this cosine rule here is one that you should know. I think that's on the formula sheet, but I'm not totally sure. So please check your formula sheet. Make sure that if this is not on it, you'll need to memorize this. Okay, and so we're getting an expression for this length L, which is the thing which is changing. And also to realize that this d theta over dt is not a variable, it's actually a constant. Okay, this constant here. Once you've got those things sort of figured out, and then you can say, okay, well, I need to get an expression for the rate at which L is changing, so I can then get that expression for L, or L squared in this case, and then derive with respect to t. So using a little bit of, well, it's not actually, yes, I suppose it is implicit differentiation, and yeah, that's giving this here, which we can then isolate dl over dt out of that to get an expression here. All right, okay folks, we'll catch you in the next one.